So let's begin this particular lecture on the buffer design. So one of the designs which we will not normally use, but I think it is very important to understand why we generally don't use this particular buffer design. So going into the next slide, so this is what we have. This particular region is our the inverter, and this one is the new design which we are talking about. So let me pick up a pointer and then start emphasizing on the different points. So this is our inverter design. So this is what we had seen, the inverter design. And we know that the PMOS transistor and then the NMOS transistor are connected in series, and thereby we were able to visualize the V output steady state voltage for a given steady state input voltage. Right. So similarly, what if if I have this kind of a the transistors configuration, like the NMOS is here and then the PMOS is here. So if I look into the left hand side and then the right hand side, you will notice that the PMOS and the NMOS transistors are completely swapped in their positions. Right. So the NMOS is now closer to the VDD rail, and then the PMOS is now closer to the ground rail. Also, but the input is very similar to what we had seen for an inverter design. Right, so what we had seen for an inverter design is the PMOS transistors was closer to the VDD rail, and we call it as, this one we said it is a pull-up circuit, pull-up. NMOS transistor was closer to the ground rail, and then this is pull-down circuit. Okay. So in this particular new configuration circuit, where we have exactly the positions of the NMOS and PMOS to be altered or to be swapped. So we have the NMOS in the on the pull up side, and the PMOS on the pull down side. Right, and then we should, and I have written here a question mark on the buffer. So we'll see what should be the output characteristics whenever we apply the input voltage. And again, we are looking into the DC characteristics. So the DC steady state characteristics, at the output side when a given in particular input voltage. Right, so this is the VDD value. So this is the VDD rail we have used. So the input voltage actually ranges from 0 to VDD volts. And for our inverter example, we have taken a VDD of 5 volts. So here also we will apply the same VDD of 5 volts, and input voltage are ranging from 0 to 5 volts. Right, in the steps of whatever, what in the inverter we had used the steps of 1 volts. So what it means is, if the input voltage is 0 volts, what should be the output voltage? If the input voltage is 1 volt, what should be the output voltage? If the input voltage is 2, 3, 4, 5, what should be the respective output voltages? And then for the inverter, we had drawn the DC, the transfer characteristics. And then similarly, what we want is for this particular circuit, for this particular buffer circuit, this particular configured circuit, we need a steady state transfer characteristics. So V output versus the V input. So this is what we want eventually. So for an input voltage, what should be the output voltage for this particular circuit? Okay, so moving forward, let's try to analyze how do we get this particular transfer characteristics. So what we really need is the current versus the voltage characteristics, especially if you can find out a current versus the output voltage, and then the intersection point should be able to map it into this particular V out versus V in characteristics. So if I actually look into this, let me pick up a different pointer. So this particular current and then this particular current. So I'm going to write this current as an NMOS current and as a PMOS current. Right. Again, these two transistors are in series, so the NMOS current and then the PMOS current should be equal. Right. So wherever the currents are intersecting, even in this particular configured circuit, I should have that as a solution point for the V out voltage, which will give me the V out voltage for a specific input voltage. right? So those particular V out voltage, I'm going to draw it in the V out versus the V input characteristics. That will be my transfer characteristics for this particular new circuit. Okay, so moving ahead, let me pick up the next slide. So this is what the new circuit is. So I'm going to write this as saying that this is my new circuit. NMOS is on the pull up side and then PMOS is on the pull down side. And I'm going to label this NMOS and the PMOS terminals. The VDD, let's pick it at, let's pick again at 5 volts. And V input voltage will range from 0 to 5 volts. V output voltage, as we had seen in the inverter also, V output voltage should range between 0 to 5 volts. So the rail is 5 volts, the rail is 0 volts here. So the rail of VDD is 5 volts, the rail of ground is 0 volts. So the V output voltage should either be, between the 5 to 0 volts. Right, it could be any value between 5 to 0 volts, any analog values also like 3.3 or 4.3 or 5.3 or 3.7, 4.7, 2.7, 1.7, 0.7 and so on. Right, so it should be any values between 5 to 0 volts. Input voltage, again, we will restrict it to not go beyond 5 volts and not go below 0 volts. So it should be between 0 to 5 volts. Because my rail, I have defined it as 5 volts, so it is assuming some kind of a, the technology node, a VDD of 5 volts has been chosen. So the V input and V output should lie between 0 to 5 volts. Now, if that is the case, if I pick the NMOS, so I'm picking this particular NMOS transistor. So what should be the terminal, terminals, the labeling of the terminals across this NMOS transistor? So which one should be drain, which one should be source, and which one should be gate? Gate is anyways, very, very intuitive. So the input that has been applied onto this particular terminal will be the gate terminal, and similarly for the PMOS also, this will be the gate terminal. Choosing the drain and the source. Now remember for the NMOS transistor, drain is always the terminal which has a higher potential than that of the other terminal, than that of the source terminal. Right, so in this case, the VDD is given to this particular terminal, right, and that is set to 5 volts. So V output can reach to 5 volts, but it can reach to 5 volts, but it should be always be in between 5 to 0 volts. So that means that this terminal is likely to be on a lesser potential than that of the another terminal. Right, so in that case, the VDD terminal, whichever VDD rail, whichever terminal it is fixed to, so that will be the drain. So this is what the drain is for the NMOS. The other terminal, the Vout terminal, which ranges from 0 to 5 volts, is likely to have a lower potential. It's likely to reach to a lower potential than that of the other terminal, and that is the reason why this is chosen as source. On the PMOS side, on this particular PMOS transistor, again we have to choose the terminals, the source and the drain. And remember that for the PMOS, the source terminal has to be at a higher potential than that of the drain. The drain, or rather, on one terminal, this is connected to the ground rail. That means that this particular potential will always be 0 volts, similar to what we had seen here. So that means the other terminal, the terminal which is connected to the Vout potential, Vout output voltage node, is likely to be between 0 to 5 volts. So it's likely to be having a higher potential than that of the 0 volts. So that's why this particular terminal is chosen as the source node, and then this one is chosen as the drain node. So now once we have the source, a drain, and then the gate terminals annotated in our transistor, it becomes much simpler for us to analyze what should be the current and how do we estimate the current, right? Estimate the current, and which current we are talking. We are talking about this particular current, and then we are talking about this particular current on the PMOS side. So we can actually estimate the current by having by writing the current equation in terms of VGS or VDS, in terms of VGS or VDS for the PMOS and NMOS respectively. Right, so that's why the terminals are, the terminals labelings are very important. Even it was important for our inverter design, and it is kind of important even for this particular new circuit configuration. So if I start writing down, in fact, even for an inverter transfer characteristics, what we had seen was, although we had the terminals labelings, we finally draw the IV characteristics in terms of the input voltage for a specific input voltage, the profile of the current with respect to the output voltage, right? So both for the NMOS as well as for the PMOS. So similarly here also, what we want to do, what we were intending to do was write down the current equation, of the NMOS and PMOS as a function of input voltage or the output voltage. So as a function of input, as a function of output voltage, right? So the same here for the PMOS also, a current equation in terms of the input and output variables instead of VGS and VDS variables. Right, so to begin with, what we have done is we have considered the NMOS transistors. So indeed the NMOS transistors are considered here, and then we will go with the PMOS transistors, and then we will see how to put the profile of the NMOS and then the PMOS current with respect to the output voltage in a one particular coordinate system, so that I'll be able to get the intersection points. Those intersection points will give us the V output voltage for the specific input voltages. Right? So to begin with, if I want to write the current equations in terms of the input and output voltages, let me try to find out what is the VGS, in terms of V in and V out. Right, so VGS for an NMOS is this one. So this is what the VGS is. So where G is connected to the input and S is nothing but the output. So VGS for an input is nothing but V input minus V output. And VDS for the NMOS transistor is nothing but VDD, which is nothing but 5 volts minus V out. So this is what the VDD minus V out turns out to be. Okay. Now what we have to do is we have to draw the profile. So let me pick a input voltage of 0 volts. If the input voltage is 0 volts here, right? When the input voltage is 0 volts, VGS, right? So V out has to be between 5 to 0 volts. So it is kind of a positive value. VGS turns out to be negative. So that means the NMOS transistor will be in cutoff. So IDS will be 0. Right? So when the input voltage is 0 volts, VGS turns out to be negative, and thereby the current will be 0 because the NMOS transistor is cut off. When V input is equal to 1 volts, V output again has to be between 0 to 5 volts. Right? And let's say that V output voltage, I'm making, so we don't know, so if V output is between 0 to 5 volts, I don't know what current it will give. So if VG, which is nothing but 1 volts here, if it is 1 volts here, the gate voltage is 1 volts here, and let's say that the V output is 0.8 volts. For some reason, it has gone to 0.8 volts, right? So V input is 1 volts, V output is 0.8. So VGS value turns out to be 0.2 volts. All right. So the NMOS will be in cutoff. In fact, the NMOS will be in cutoff for any values of V out above 0.7 volts. So any values, above the V out goes above 0.7 volts, it will be in cutoff, and that's what I've written. V out any above 0.7 volts, NMOS will be in cutoff, and any values below 0.7 volts, right? So this particular V out, any values below 0.7 volts, I will have the NMOS giving the current. Okay. So NMOS giving the current. So let me try to see whether I can erase some of these diagrams. Okay, on resuming this, so what we were, so we were at the NMOS and the PMOS transistors, and let's say that what we wanted to say is, if this is 1 volts, so let me pick this pointer, say that this is 1 volts, and V out is, let's say it is 0.5 volts. Right, so the VGS value in this case, the VGS value, so I'm going to write it here, VGS value turns out to be 0.5 volts, and the VDS value is actually 4.5 volts. Which says that the VDS is much greater than VGS minus VT. VGS minus VT turns out to be 0.2 volts and VDS value is anyways 4.5 volts. So it is much higher, right? So in that case, this will be in saturation, right? So no matter what is the output voltage, if it is less than 0.7 volts, the VDS value of the NMOS transistors, so the VDS of the NMOS transistor will always be much higher than that of the VGS minus VT, and hence the transistor, this particular current for the NMOS transistor will always be in the saturation. So I'll have to write the saturation current equation, right? So this will be the NMOS in saturation. If the Vout value is anyways greater than 0.7 volts, the NMOS will be in cutoff. All right. So similarly, when V input voltage is 2 volts, so instead of 1 volts here, if we change it into 2 volts, and V output is actually greater than 1.7 volts, then the current will be 0 because the NMOS transistor will be in cutoff because VGS will be less than 0.3. Right? V output, if it goes beyond 1.7, NMOS transistor will be in cutoff, so the current will be 0. Right? So that is what this line says. Anything below 1.7 volts, V output, anything below 1.7 volts, right? So the minimum value of this will be nothing but V out will be 0. So that will be 2 volts. VGS will be 2 in that case. But VDS will anyways be 5 minus 0. So that will be much greater than VGS minus VT. So that means the NMOS will be in saturation. So VDS greater than VGS minus VT will always give the NMOS transistor to be in saturation. Similarly, when V input is equal to 5 volts, V output, right, if it is greater than 4.7 volts, NMOS will be in cutoff. If it is greater than 4.7 volts, NMOS transistor will be in cutoff and the current will be 0. And if it is less than 4.7 volts, 4.7, so let's say that, if it is somewhere around 3 volts and then the input voltage is anyways, we have taken it as 5 volts. So the difference VGS is nothing but 2 volts and this is 3 volts. So VDS value will be 5 minus 3 volts. So VDS is 5 minus 3, VGS is 5 minus 3. Right, so but VDS will be greater than VGS minus VT, so NMOS transistor will be in saturation region, and that's what we have stated here. So even if it is smaller than 4.7 volts, it will be in the saturation mode because VDS is greater than VGS minus VT. Right, so hope you have understood this working. So what we have seen is we have considered the NMOS transistor in this particular new circuit and applied the different input voltages 0 volts, 1 volts, 2 volts, 3 volts, 4 volts, 5 volts, and saw that the NMOS transistor will either be in cutoff region based on a particular value of the V output voltage, or it will be in the saturation region based on the specific range of the output voltage. Right, so for a different input voltages, we have a specific range of the output voltages where the NMOS transistor will be in cutoff and a specific range where the NMOS transistor will be in the saturation region. So this will help us in drawing the current profile when we draw the current profile with respect to the output voltages for a specific input voltages. Right, so that will be for the NMOS. Now let's take a look at the current profile. Considering the NMOS transistor, I have taken 2 such cases. One is the input being 5 volts and then the input being the 1 volts. The all other values, input being 2 volts, 3 volts, 4 volts will be very similar, and that's why I have selected 2 such cases. For an input of 0 volts, for an NMOS, the input of 0 volts, the current was anyway 0 for an NMOS. Right, so I have not taken that. So I have selected 2 of the cases where input voltage is 1 volt and input voltage is 5 volts. So for an output voltage greater than 0.7 volts, we know that the NMOS transistor will be in cutoff, so it is 0 value. For anything lower than 0.7 volts, for the output voltage, the current will be in saturation region, the NMOS will be in the saturation region. So the saturation current is nothing but beta n by 2 VGS minus VT the whole square. So VGS minus VT the whole square. So this one I have written VGS as nothing but input of 1 volts. 1 volts source side, it is connected to the Vout. So 1 minus Vout is nothing but VGS minus of 0.3. So I'm assuming that this is a 65 nanometer technology node, and then VT is nothing but 0.3 volts. So I'll get beta n is equal to nothing but beta n by 2, right? 0.7 minus V out the whole square, right? Similarly, when V input is equal to 5 volts, input is 5 volts, V output, if it is greater than 4.7 volts, the current will be 0. If it is smaller than 4.7 volts, the saturation current is nothing but beta n by 2. So this one, input voltage is 5 minus the source potential is V out minus of 0.3 is the VT. So beta n by 2, 4.7 minus V out the whole square is what we will get, right? So if I want to draw the profile, if I want to draw the profile of the current versus the V output for different V input voltages, right? So if I pick 5 volts, this is the 5 volts input voltage. V output, if it is 0, right, from 0 to 4.7 volts, from 0 to 4.7 volts, this is the current. And beyond 4.7 volts, it is the 0 current. So when it is 0 volts, output voltage is 0, my current is actually 4.7, the whole square. Of course, there will be beta n by 2, right? When my output voltage is 1 volts, right, it will be 3.7, the whole square. When my output voltage is 2 volts, right, it will be 2.7 the whole square. So it is, in fact, it is decreasing, it is a decreasing second order decreasing profile. Second order in the sense, the second order is coming from this particular, inversely, or rather, it is decreasing in a square profile, right? So this is what we should be getting, where at this particular point, it is touching the 0 value, right? That will be the value of 4.7 volts. Right? So at 1 volt, it is nothing but beta n by 2, 3.7 the whole square. Similarly, this particular point, it will be beta n by 2, which will be 2.7 the whole square. And then so on. And then it touches 0 at 4.7 volts. Right? Hope this is clear. So this is the overall graph I've drawn. In the previous slide, I have drawn only for V input of 5 volts. V input of 5 volts. This is what I had drawn. Right? Starts from 4.7 the whole square beta n by 2 or beta by 2, and then it reaches to 0 at 4.7 volts. Right? Similarly, input voltage of 4 volts, it will start from 3.7 the square beta by n, beta by 2, and then it touches to 0 at 3.7 volts. And similarly, V input of 3, it starts from 2.7 square beta by 2, reaches to 0 at 2.7 volts. V input of 2 starts from 1.7 square beta by 2, the highest value, and then touches to 0 at 1.7 volts. Although, this graph, I've just drawn it as though it is touching well before 1.7, but let's say that it touches at 1.7. And then similarly, V input of 1, the highest value will be 0.7 square beta by 2, and then touches to 0 at 0.7 volts. Right? And V input of 0 is nothing but a straight line, because V input of 0 is nothing but a straight line because the current is anyway 0, NMOS transistor. And if I am considering the NMOS transistor, the current will be 0.